So the fourth and final topic today is going to be looking at the differences between reentrant locks and non-reentrant locks and when it matters. And it turns out a lot of times it doesn't matter, but whenever you have data structures that have inherent recursion in their call chains, this happens a lot with object-oriented frameworks, for example, that have callbacks that still have to call back into the framework, then the choice of reentrant versus non-reentrant locks makes a big difference. So this particular example is there to demonstrate this issue. And I guess you could kind of classify this as another example of a frequently made mistake if you don't understand the subtlety about recursive locks versus non-recursive locks. So let's go ahead and share the screen. Probably first should go back to my Wikipedia, or sorry, to my live lessons repository. This is in EAX24. This is the EAX24 example. Okay, so in EAX24, we have a cool little framework here, which is basically a variant of the countdown latch that's provided on Android, which is a really helpful little class. Or it's not a countdown latch, a countdown timer. This example uses a countdown latch. But countdown timer is basically a way to schedule an object that will get called back periodically every so many milliseconds into the future, so many times. And every time the timer goes off, it does a callback on an on-tick method. And then you can do things like you could update a GUI display to have a timer, like a countdown timer, like a stopwatch, for example. So that's what a countdown timer is. So it's an interesting, cool little mechanism available in Android. So I just have a port of it here. And here's basically how it works. And you'll see very quickly why reentrant locks matter in this particular context. This particular example is a microcosm of issues that arise in object-oriented frameworks when you have callbacks that come out of objects registered with the framework, and in the callback calls back into the framework. And we want to make sure that we're not going to end up deadlocking on ourselves, so-called self-deadlock, when locks are held across the boundaries of callbacks. So we're going to have a field that keeps track of the milliseconds since when the alarm should stop. So we're basically going to keep track of this. We're going to have the countdown interval, which says every so often count down. So for example, we might say, for the next 300 or next 30,000 milliseconds, count down every 1,000 milliseconds. So for the next 30 seconds, count down once a second. So that's what those values are. We use a scheduled executor service to do this. It's a scheduled thread pool executor with a pool size of 1. And then we've got some things we use to stop the timer. We'll see how that gets used. We can keep track of if we've been canceled or not. And then we've got ourselves a lock. And this particular lock, as we'll see, is cleverly done to be a couple of different kinds of locks. So here's the countdown timer itself. You take the lock, we store the lock, we take the number of milliseconds in the future, we take the countdown interval, we stash those away, we start up the thread pool executor service with the scheduled executor service to have a timer, we set the policies to some coherent values, and now we go ahead and look at the methods. So here's the start method. This starts everything in motion. And when the start method is called, it acquires the lock to make sure we have exclusive access to those fields, indicates we haven't been canceled yet, figures out if we're starting and we're already done, which would be weird, but we have to handle that. And then we figure out when we need to stop. We schedule the initial timer, and then we return this so we can chain these things together with a fluent interface. And because we're good users of the try finally idiom in Java, we make sure that we always unlock our lock no matter how it is we're leaving this particular scope. So that's what start does. Here's cancel. This could be called when an application says, I don't want this thing to count down all the way. I want it to stop at a certain point. So what we do there is we grab the lock, we set the flag to true, we shut down the scheduled executor service right now, and then we release the lock. Notice that this lock call is called in response to a call from an application. And that application itself may have been dispatched by a callback coming out of this countdown timer. And here is that callback. That callback is the on-tick method. And on-tick is an abstract method. It's a hook method that's going to be called back by the underlying framework every time the tick timer expires. We also have an on-finish method where we can kind of clean things up. So here's the interesting part that's doing the logic with onTick. So this is called scheduled timer. And you can see what it does is it goes ahead and it creates a new runnable, and it's going to run that runnable. It'll run in the background. And I think this code is pretty much copied from Android. So yes, we have to use a runnable because we access this. So you'll see that in a second. So the run method here grabs the lock, checks to see if we're canceled. If we're canceled, we're done. If we aren't canceled, we figure out how much time is left from our original start time. If there's no time left, we call the onFinish hook with the lock held. If there's time left, we figure out the last tick start. We need to use that to recompute things when we get back from the onTick callback. And then we dispatch the onTick method. And this is where the problem can arise. Notice how we keep this lock held across the callback to onTick, which means if onTick calls back to cancel, then if we don't have a recursive lock or a ReentrantLock, we're going to deadlock on ourselves. So keep that in mind when we look at the actual application. When onTick returns, we figure out how long tick was running, and that tells us the amount of delay we need to use. And then we go ahead and do some magic computations to figure out how much longer we should go. And then we reschedule this runnable to be called back at this delay at this many milliseconds in the future. So this will get called back. This method, this run method here, the run method there will get called back. And you'll notice that once we're done, as always, we unlock the lock. So we unlock the lock when we leave the run method, but not before. So the lock is held across callbacks. And then down here, we go ahead and we schedule this timer handler, which was this runnable. We start the ball rolling by scheduling it to run right now. So we're going to start off right now, of course, is relative, but we're going to run it as soon as the scheduler can run it, and it'll call back and set the wheels in motion. Okay, so that's how the countdown timer works. Now let's go ahead and take a look at the driver program that uses this. We're going to use a countdown latch to kind of control the tests. We're going to first do this using a ReentrantLock, which of course will be the Java ReentrantLock, which is reentrant. So you can basically do lock calls even if you, the current thread, already hold the lock. And then we're also going to have another variant that runs that's going to use a non-reentrant lock. Now, I had to do a little wrapper for my non-reentrant lock, and we'll take a look at that in a second. And then we go ahead and we basically wait for up to 10 seconds for this thing to work. So let me show you what it does when I run the code. First thing we do is we're calling it with the ReentrantLock, so it all should be well. So you can see it went ahead and finished cleanly. And then we're going to go ahead and run the non-reentrantLock, and as you can see, it's hanging here, and that's because it's stuck in self-deadlock. So let's go ahead and take a look and see why is it stuck in self-deadlock. So here is the non-reentrantLock. The non-reentrantLock implements the lock interface, and then we go ahead and make ourselves a stamped lock. Now, if you're a student of Java 8 synchronizers, you know that stamped lock is very cool, but it does not support reentrant semantics. That's one of the things that makes it faster than the abysmally slow reentrant read-write lock that came with earlier versions of Java since Java 5. So the lock method here simply goes ahead and gets a write lock, lock interruptibly, gets a write lock, try lock does a try write lock, and we can do that a couple different ways. There's a timed version of this, and unlock unlocks the write lock. So that's basically just defining the lock interface and then mapping it to the underlying stamped lock implementation. But the problem is stamped lock is not reentrant. So in this situation where the runnable's running and the lock is held and the onTick method gets called back, we're going to have some problems. And the problem, of course, is that the onTick method is going to end up doing a cancel. So let's see if we can. So basically what's going to happen is on the onTick call, we're going to go ahead and basically self-deadlock on ourselves. So that's the problem that we're running into in this particular case. And you can see how it works. Here's the test countdown timer. We pass in the lock and the other information. We make ourselves a new countdown timer, and we override the onTick method. So this is why we get ourselves jammed in the first place. So the onTick method for this thing is going to check to see whether or not enough time has elapsed. And once enough time has elapsed, after it's about halfway done, we go ahead and cancel it. And then we go ahead and decrement the latch so we can return. So when we do the cancel here, this call ends up calling back into the countdown timer. And you can see, because we have to preserve the integrity of the internal state, the shared mutable state, cancel calls lock. So that's where we're going to get ourselves into trouble when we use the non-reentrant StampedLock, because of course it doesn't work that way. And so it'll just basically deadlock on itself, which is a very interesting design decision, but it was intentional. That's the way that they designed StampedLock to work. So hopefully you learned a few interesting things. Basically, if you want to use advanced synchronizers like StampedLock, make sure you don't have a situation where you have to use them in reentrant code where you have callbacks. Otherwise, you can get stuck, as we have seen here. Okay, so let's see if there's any questions about this topic. Let's see. Is there a happens before relation between volatile read and volatile write? Yes, absolutely. That's kind of the whole point of volatile, in fact. You can think of volatile as sort of like synchronized on data. So volatile is basically synchronized reads and writes on data. It's not implemented that way, of course, but it's along those lines. So basically, there's a happens before relationship enforced for that. Line 107 could be outside the scope of the lock. Let's see. So let me go back to line 107 and see what it's doing. Share my screen. And where to go? So it must be line 107 of the countdown timer, maybe? I'm not quite sure what the question here is on line 107. You'll have to give me a little bit more of a pointer, please. Could it be outside the scope of the lock? Oh, so well, part of the question is, could we use synchronized instead of ReentrantLock? Sure, but then I couldn't write my test the way I did because, of course, you can't pass synchronized statements around as parameters to classes and methods the way we've done here. So that's part of your question is, why did we use ReentrantLock, not synchronized? I could have created my own synchronized ReentrantLock, but remember, synchronized is really a syntactic element baked into Java, the language, not baked into Java, the class library. So that's one reason why we did that. Why is this doing this to me? Let's see. Okay. So I wasn't quite sure about the question about the scope of the lock. The JCP, the Java Concurrency and Practice book recommends we should not call alien methods while holding the lock. That's probably a good advice. Is it a good practice to invoke tick while holding the lock? Yes, you absolutely have to hold that lock. Otherwise, strange things can happen and you can have a different set of problems. There are ways around that, but they're very complicated. And the code I have there, the countdown timer, is just straight out of Android. So they're doing that. It's a very common technique to hold the locks across callbacks. You just have to make sure that you are careful. Let's see. In order to call shutdown now, oh, I see. Now I understand your question. So it's this part here. We probably could move that part out of there. I don't think it did any harm keeping it in there, but it probably could be moved out. That probably wouldn't. Although I should really go back and look and see the way it was done in Android. I'm really trying to keep my code here as close to what Android does as possible. I think that's probably the way it worked in Android, which is why it's there. You probably could move it out, but why risk it? So it's not doing any harm. You're shutting things down. That's rarely the time critical part. That not being able to parallelize that piece of code is probably not the end of the world, especially because after this thing is called, everything's going to shut down. So yes, it probably could be moved out, but I don't think the Android code did it that way, and I didn't feel like taking the time to analyze why it was done that way. But it's an interesting point. Okay, so that was that particular topic.